Hi, this is Professor Stuckard, and in this video we're talking about maximums and minimums. Now, maximums and minimums are pretty much the same idea as when we saw them back in Calc 1. A maximum is the biggest point and a minimum is the smallest point, except, again, we're mostly concerned about local maximums and local minimums, which means it's just a maximum or a minimum around a small area, right, or a specific point on the graph. And our definition makes sense too, right? A minimum is less than or equal to all other points near that spot, and a maximum has to be bigger than or equal to every point around that particular spot. So just like when we are talking about maximums and minimums with functions of one variable, it's very similar with two variables, where what we're really looking for first is going to be our critical points. So a critical point for a function of two variables occurs if the partial derivative with respect to x is 0 and the partial derivative with respect to y is 0. It means they both must be 0. Now, with our gradient notation, we can actually make this a little bit easier and say that the gradient at that point must be the 0 vector. And again, this is very similar to when we talked about maximums and minimums and critical points back in Calc 1, where when something has a slope of 0, that means it has a horizontal tangent or is neither increasing or decreasing at that point. Now, we could also define a critical point to be where the partial derivatives do not exist, and that is absolutely also valid, but we're not going to really deal with that too much in this course. Now, the important part about critical points actually comes from our theorem that if a point is a local minimum or a local maximum, then it must be a critical point. And just like in Calc 1, we need to make sure that we recognize that the converse of this statement is not true. Basically, not every critical point needs to be a min or a max. Every min and max needs to be a critical point, just not the other way around. Kind of like how every square is a rectangle, but not every rectangle is a square. Now, the way we're going to tell whether or not our critical points are maximums or minimums or something else is going to be with our second derivative test, which is the same exact idea from Calc 1, because the second derivative tells us concavity. Now, because we're dealing with partial derivatives in this case, that means there's multiple second derivatives. And so our second derivative test has to actually include all 4 of our second partial derivatives. And so our second derivative test, we're going to be calculating what we write as d. All right, and so d is a function itself, and it's going to be the second partial xx times the second partial yy minus the second partial xy squared, or basically 2 of them. Now, if you want, you can memorize that as the determinant of a matrix. That makes it easier. I don't know if it necessarily does or not. And then the idea is that if I use my second derivative test now, based upon this, if that value d is positive. So if it's positive, that means that my first 2 partials, xx and xy, must have the same sign, which means that the second partial derivative xx and the second partial derivative yy, it means the concavity is going to be the same concavity both in the x direction and in the y direction, which means that if we know that our second derivative test yields a positive result, we then check just one of the second partials to figure out whether they were either both positive or they were both negative. And then, again, the same way concavity worked in Calc 1, if my second derivative is bigger than 0, if it's a positive value, then that must be a local minimum. All right, and again, it goes back to just concavity. If the second derivative is less than 0, the second derivative is negative, then it is a local max. All right. Now, again, the formula says to check the second partial xx. You could swap that out for x, or you could swap that out for yy, because we know that they have the same sign if d is already positive. And so again, cases A and B tell us whether it's a min or a max. Again, when we calculate this formula, we get a positive value. Now, if we calculate our formula and d is less than 0, meaning d is negative, that means that our ordered pair is what's known as a saddle point. That means that my concavity in the x direction, my concavity in the y direction are actually opposite concavities. And we'll talk about that in just a second. And then, of course, if d is 0, well, the test is inconclusive. But let's go back to the saddle point. So a saddle point is going to be our critical point on a surface where the surface is increasing in one direction, but decreasing in another. And so the most common type of saddle function is this hyperbolic paraboloid, where z equals x squared minus y squared. That red point 0, 0 is a saddle point because as I move in the x direction, my function is increasing. And again, you can see with that orange arrow that my function is definitely getting bigger, it's increasing. But it is going to be decreasing in the y direction, which is my green arrow. And again, it kind of looks like a saddle, so it's a saddle point. So again, imagine like a saddle on a horse in a Western movie, right? The saddle goes over the horse one way, and then you sit to stay in there, and yeah, that kind of looks like a saddle. And so we call those saddle points. So let's do an example of how I would find and classify all critical points for a particular function. So given this function, 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2, how am I going to find and classify the critical points? All right, so first of all, you should absolutely do this entire problem on a separate sheet of paper. Write down the function, don't use my notes, and work through this with me. All right? Let's make sure we're doing the algebra here. Now, the first step is let's find all those first and second partial derivatives. We're going to need the first derivatives to find our critical points, and then we're going to need our second derivatives to classify them. So we might as well do everything at the same time. So go ahead, pause the video, and find the first partial with respect to x, and the first partial with respect to y. Then find the second partial xx, the second partial yy, and then of course the partial xy. And if you've done that, well, hopefully we got to the partial with respect to x, 6xy minus 6x, and the first partial with respect to y is 3x squared plus 3y squared minus 6y. And then the second partials. Partial xx is 6y minus 6, partial xy is 6x, and partial yy is 6y minus 6. Now a few things. First of all, the partial xx and the partial yy, they're the same in this particular example, but that's really not always the case. This is a specially crafted example to make life a little bit easier later on. They're typically not going to be the same, so please don't expect that. Also, this is a great place to check Clairaut's theorem. If you start with the partial with respect to x, if you take that partial with respect to y now, well, yeah, you should get 6x. And if you started with the partial with respect to y and you took that derivative with respect to x, you better still get 6x. And again, it's just a good thing to, well, practice and make sure we're still good at. Well, now we have to find those critical points. Now, again, the critical points have to make both of our partial derivatives 0. So we're setting both of our partial derivatives equal to 0. So now we have a system of two equations with two variables, x's and y's. Now, there's probably a couple of different ways you could go about doing this, but the easiest one, I think at least, and feel free to search YouTube for other video examples of people doing it different ways and see if that works better for you. But I know that, again, it must make both of those partial derivatives 0, so let's start with the easier one. And when I look at those two partials, it looks to me like the partial with respect is going to be the easier one. And then since it's set equal to 0, well, we're going to use the zero product property, meaning that the only way to be able to multiply to 0 is if one of your factors, or both of your factors, are 0. So we're just going to factor. And so we can see if I take my partial with respect to x, well, I've got a common factor of 6x. And if I factor that out, I get 6x times the quantity y minus 1. And now I'm going to solve each of those equal to 0, which of course is going to yield the two solutions, x equals 0 and y equals 1. All right, so what we know now, again, is our partial with respect to x. If my x coordinate is 0, well, then my partial is 0. My y coordinate is 1. My partial is also going to be 0. So these are two potential solutions, but I need both of my partials to be 0. So I need to take the result from looking at the partial with respect to x and plug that into my partial with respect to y. All right, so we take my partial with respect to y and substitute, and we'll do the first one, x equals 0. We're going to have to do both cases, but we'll start with x equals 0. So plug in a 0 for the x, which makes that 3x squared term just, well, go away. And now we need to solve when this is going to be 0 for the rest, which is 3y squared minus 6y. All right, well, again, let's factor. I got a common factor of 3y. My GCF is 3y, so I factor that out. And then if I solve both of my factors equal to 0, I'm going to get two solutions, either y equals 0 or y equals 2. So what that means is that, again, if my x-coordinate is 0, my partial with respect to y will be 0 as long as the y-coordinate is either 0 or 2. We also know from the first part that as long as x equals 0, the partial with respect to x is 0. So that gives me two critical points now where I know both of my partials are going to be 0. 0, 0, and 0, 2. Again, the x-coordinate is 0, and then my y-coordinate is 0 or 2. Well, now I would do the same thing with my other possible solution, which is y equals 1. So I take my partial with respect to y, and now I'm going to plug in y equals 1. Well, if I plug in y equals 1, 1 squared is, well, just 1, so it's just 3. 6 times 1 is 1, so 3 minus 6 is minus 3. And again, we're going to factor. So I have 3x squared minus 3, factor the 3, that leaves me with x squared minus 1. I have a difference of 2 squares, piece of cake to factor that, x minus 1, x plus 1. So my two solutions now are going to be x equals 1 and x equals minus 1. All right. And again, you should be pausing the video and solving these yourself. And then, well, I have two solutions here. And again, I'm going to get two more critical points. Now my critical points are going to be 1, 1 and negative 1, 1. Again, the y-coordinate is 1 for both of them, but now we've solved for the x. So now basically the last step is to find my function d using that second derivative test, plug in each of my critical points, and then classify them based upon, well, that rule we saw just a little bit earlier. So again, we're going to multiply the second partials with respect to xx and xy, or xx and yy together. And in this case, they are the same function, which is why I just have 6y minus 6 quantity squared, and then minus the partial xy squared, so minus 6x squared. So I'm going to test the order pair 0, 0 first. And if I plug in 0, 0, make everything 0, well, 6 times 0 is 0. 0 minus 6 is negative 6. Negative 6 squared is 36. And, well, the other part is 0, so I just get 36. And again, I don't particularly care about the value. I don't care that it's 36. I just care that it's a positive number. Because if it's a positive number, well, that means the concavity's got to be the same in both directions, which means it's either a min or a max. So now I check that concavity in the partial xx or the partial yy. Again, you can choose whichever one's easier, although in this case it's the same. And the partial xx, if I plug in a 0 everywhere in my 6y minus 6, I get, well, negative 6, which is less than 0, which is negative. And so if we look back at our table, of course, a negative second partial means we have a local max because we're concave down. So that means the order pair 0, 0 must be a local max. Now we're going to follow the same exact process, but now let's test our order pair 0, 2. So again, do this on your own. Plug in 0, 2 into the function we found for d. You should just end up with 6 squared as your result, which is positive 36. And again, all I really care about is the fact that it's positive here, which means now I have to plug in that ordered pair into my second partial xx. But when I plug that in, 0, 2, well, 6 times 2 is 12. 12 minus 6 is 6. So it's positive, which means 0, 2 must be a local minimum point. Next up, let's test 1, 1. And again, do this on your own, but when I plug in 1, 1, 6 times 1 is 6. 6 minus 6 is 0. 0 squared is 0, so that entire part goes away. All I'm going to be left with is minus 6x squared, So again, be very, very careful that you're paying attention to your negative signs and you're doing this neatly and writing this out. And yeah, that means this is probably going to take an entire page, but you know, it's better to get the right answer and take a while than to get the wrong answer quickly. And if I get minus the quantity 6 squared, that's going to be negative 36, and that's less than 0. If that's less than 0, again, that means I have two different concavities, which means this is a saddle point. The ordered pair 1, 1 is a saddle point. Last up, only one more point to check, and that's the ordered pair negative 1, 1. When I plug that in, I'm going to get minus negative 6 squared, which is minus positive 36, or just negative 36. Again, that's less than 0. So again, this is a saddle point. And so we've now classified all 4 of our ordered pairs as maximums, a maximum, a minimum, and 2 saddles. Now let's actually use GeoGebra to take a look and see if that really matches up with what we found. So here, I plotted my function in GeoGebra. Here it is here. And we can take a look and we can see that, well, we actually did everything the right way. So my first order pair that I tested, 0, 0, is right here. And we can see that 0, 0 is definitely going to be a maximum. I have a maximum right here at 0, 0, where my local maximum is the value 2. Now, it's clearly not an absolute maximum because, look, my function is growing without bound on this side, but it is definitely going to be a local max at that ordered pair 0, 0. Similarly, we can see that, oh, down here is definitely going to be my local min, and that'll be at the ordered pair 0, 2. Again, the green one is going to be my my axis there. So we now have our maximum point and our minimum point, and then the other ones we looked at were going to be 1, 1 and negative 1, 1. Well, if I look at this straight up and down, well, here's 1, 1 right here. And again, if we kind of tilt this, we see that this is definitely going to be a saddle point. It's going up in this direction towards my maximum in one direction, but it's going down and decreasing in the other direction. This is absolutely our definition of a saddle point. And if I spin around over here for the ordered pair negative 1, 1, well, I see the same thing. And I can see that it's definitely increasing in my one direction, but decreasing in my other. And that's the definition of a saddle point. And yeah, I'm pretty confident we did that whole part correctly. We're going to wrap up here with a few definitions and a theorem. And so we're talking about regions in space. We say a region is closed if it includes all of its boundary points. Now, this is kind of the same, but we have just intervals. We say an interval is closed, or we use our square brackets, if we include our endpoints, which are our boundary points. Now, in 2 dimensions, our boundary points for our region is actually the outside of it. And we talked about this a little bit when we talked about domains of our rational, or of our functions of 2 variables as well. Now, a region is open if it doesn't include them. And again, that's similar to if I have a region in space that doesn't include its boundary points, it doesn't include the outside edge, just like when we have an open interval, we're not including the endpoints either. Now, there are going to be regions that are neither open nor closed. They include some of the boundary points. So it's not entirely open, it's not entirely closed. And our last definition is we say a region is bounded if it is finite. Now, a finite region, that should be fairly intuitive, but again, if you're going to be doing rigorous mathematics, or you're a math major and you eventually end up taking topology or you study spaces more in depth, what this really means is that your enclosed region, your bounded region, can be basically circled. You can put a gigantic circle, you can make a disk and enclose your entire region inside that disk. So visually, we would represent this. So if I have something open, we use that dashed line. So that pink one over there is an open disk with a dashed line. The one on the right is a closed region. So again, our regions can be as complicated as, well, we want to make them. And as long as we have that solid line, it is a closed line. And our boundary is, well, the outside edge. And our boundary point is any point that's on the edge. And then, well, anything on the inside of my region R is an interior point. We can definitely tell that this is a bounded function as well because, well, look at that. I just drew a circle, and my circle enclosed the entire region. That's how I know it's bounded. Now we have a few definitions. The last thing we're going to talk about is the extreme value theorem. If my function is continuous on a closed bounded region, that means there must be an absolute minimum and an absolute maximum in that region. Now, again, we can apply our same derivative test to find our critical points, and we would just have to also test our boundary as well to actually apply this, well, in an actual example. Again, not too worried about that right now. Again, focus more on using the second derivative in the second derivative test. And if you have any questions, as always, please send me an email.